Today we're going to talk about functions and inverses. Recall that a relation is just a set of ordered pairs. A function is a relation in which for each distinct x value there's exactly one corresponding y value. So for every input there's only one output. If a function f is a set of ordered pairs x, y, then remember the inverse of f is the set of ordered pairs y comma x. When the inverse of a function itself is a function, then it's said to be a one-to-one function. So recall that a one-to-one function, so a function is one-to-one if every output corresponds to exactly one input. And if a function is one-to-one, then we say its inverse is a function. So remember that when we are looking at this graphically, we can use what's called the horizontal line test, which we talked about one-to-one functions and horizontal line test last year in our inverse unit. So the horizontal line test, a function is one-to-one if and only if no horizontal line intersects the graph of f more than once. Kind of like your vertical line test, but this is used on your graph of f to see if the inverse is a function. If you want to see if the actual graph is a function, you would use the vertical line test. So we're going to go ahead and look at these mapping diagrams below. It says justify each mapping with an observation. So remember, your domain are your possible x values and your range is your y values. So here, notice that each x value corresponds to one y value in the reverse. So this says it's a one-to-one function. So if we go back to our definition of one-to-one function, every output corresponds to exactly one input. So we could say each output y corresponds to one input x. The next one says not a one-to-one function. So again, same thing. If we look here, notice that we have two input values going to the same output value. So again, the definition of one-to-one is every output corresponds to one input. So this is not one-to-one because both x equals 1 and x equals 2 have the same outputs, which is y equals 4. So if you were to graph this, it would fail the horizontal line test. And then this next one, we can see that we have, again, our domain and range, and it says it's not a function below. So this is not a function because remember the definition of function is for every input, you have only one output. So not a function, x equals 1 has two output outputs, y equals 4 and y equals 5, which means this fails the vertical line test if we were to graphically look at this. All right, so let's actually find the inverse graphically. So we're given the graph of f of x shown. It says to graph the inverse and describe the relationship between the function and its inverse. So remember, when you're graphing the inverse, you switch your x and your y values. So whatever your y values are, those are going to become your x values. So this would be 5, 0, -3, -4, -3, 0, 5. And your x values become your y values. And notice that right here we have this notation, f to the -1 power of x. Remember, that means f inverse of x. It's just the way of saying the inverse. So that means this is our inverse function. So now we're going to take our x values and those become our y values. So -6, -5, -4, -3, -2, -1, and 0. And then we're just going to go ahead and graph these points. So we have, I'm going to start with the vertex, which is at -4, -3. And then from there we have -3, -4, and -3, -2, 0, -5, 0, -1, 5, 0, and 5, -6. All right, so looking at these graphs, we're going to answer some questions or talk about some things. So f of x, looking at our original graph, so remember this is f of x and this one is f inverse of x. We know that it's a function because it passes the vertical line test. So f of x is not 1-to-1 because it does not pass the horizontal line test. So if I would take a horizontal line on this graph, and if it hits anywhere in 2 spots, then you know it fails. So in this case, it fails in a lot of spots. So it fails the horizontal line test, so it's not 1-to-1. Because of that, without even graphing our inverse function, we already know that the inverse is not going to be a function because of that. So anytime your original graph fails the horizontal line test, you know the inverse is not a function. So then when we actually graph the inverse function, you can look now and say, oh yeah, this is not a function because if we were to use the vertical line test, it would fail the vertical line test. So VLT just stands for the vertical line test. So that's how you would graphically look at your inverses. So graphs of inverse functions are reflections across the line y equals x. Given a function f of x, the notation for the inverse function, which we just talked about, is f inverse of x. You do it to the -1 power. Remember that does not mean that you have 1 over f of x. That is not what you're doing, so don't make that mistake. This is an inverse notation. The domain of the function is equal to the range of the inverse function, and the range of the function is equal to the domain of the inverse. So if we go back up here to this graph, we can see the domain of this graph is all real numbers because it's a quadratic function, which means then the range of this graph is going to be all real numbers. Then if we go back and look at the range of our original f of x graph, the range starts here at -4, so bracket -4 to infinity. And then that means this becomes the domain. So you can see the domain is bracket -4 to infinity. So the domain and range switch. Which of the following graphs are 1-to-1? Which of the following functions will have inverses that are also functions? So take a minute to pause the video and do this on your own and then unpause when you're finished. So looking at the first one, this graph is a 1-to-1 function because it passes the horizontal line test. So because it is a 1-to-1 function, that means the inverse is a function. We just talked about quadratic graphs. This is not a 1-to-1 function. It fails the horizontal line test, which means the inverse is not a function. This graph is a trigonometric function, so this is not 1-to-1 because it fails the horizontal line test. It would hit in multiple spots more than once. And so that means the inverse is not a function. But if you were to look at all 3 of these graphs and ask if these were functions themselves, yes. So all 3 of these graphs pass the vertical line test. So algebraically, how do we find the inverse? So remember, when you're algebraically finding the inverse, you replace f of x with y and switch x and y and solve for y. And so again, I didn't realize we put it down here, but this notes that these 2 things are not the same. So if the inverse is a function, you can replace y with f inverse of x. If it's not, then you just keep it as y equals. So looking at this first one, we then take f of x out and we're going to replace that with y. So that becomes y equals 3x minus 2. Then for the inverse, you switch your x and your y's and solve for y. So when you're solving for y, you're going to use PEMDAS backwards. So when we simplify, we use PEMDAS in that order, but when we are solving going the opposite direction, we're going to go backwards. So you look for things add or subtract to the variable that you're trying to solve for. So we're trying to solve for y. So we're going to get rid of that 2 first by adding the 2 to the other side. So that gives us x plus 2 equals 3y, and then we get rid of things that are multiplied or divided. And so now if you look at the original function, it's a line which passes the horizontal line test. So the inverse we already know is going to be a function. Or you can look at the inverse equation. So you can see that passes the vertical line test. So this is a function, so we can use our inverse function notation. And usually you want to write it in the form that you're used to. Like, so if it's linear, y equals mx plus b. Quadratic, we can write in standard form, etc. So for this one, I have 1/3 x plus 2/3 for my inverse. So the slope is 1/3 and the y-intercept is 2/3. Looking at the next one, same thing. So we're going to go ahead and switch our x and our y values. So this would be x equals y cubed minus 5. And then we solve for y equals. Remember, you're doing PEMDAS backwards. So we don't get rid of that cube power. We would first want to add the 5. And now we can get rid of the power because you do addition, subtraction, multiplication, division, exponents, and then parentheses. So now we have the exponent, which gives us the cube root. And so this, remember, is a cubic function, which would be moved down 5. So if I just draw a quick picture, my graph will look like this, which that passes the horizontal line test, which means the inverse is also a function. So f inverse of x equals the cube root of x plus 5. The next one, same thing, switch our x and our y values. Now, this one's slightly harder because notice that this is a quadratic function that we have, y squared plus 4y. So remember, we've learned to solve quadratic equations. When we want to solve a quadratic equation, we can solve it by factoring, we can solve it by completing the square, we can solve it by using the quadratic formula. So in this case, if we factor this, the only way that you would factor it, this would be x equals y times y plus 4. But that doesn't get y by itself. So since it doesn't get y by itself, in order to solve this one, we could complete the square, or we're going to go ahead and use the quadratic formula because most of you are used to that. So recall x equals negative b plus or minus the square root of b squared minus 4ac all over 2a is our quadratic formula. And in this case, because our y is squared, because we switched our x and our y's, we're using our coefficients as a is equal to 1, b is equal to 4, and then notice this is not set equal to 0. So whenever we use the quadratic formula, you want your equation set equal to 0. So that means we would have to subtract x to the other side. So that means that our constant in this case is negative x. So when we plug this into our quadratic formula, because it's y squared, we're doing y equals, not x equals. So y equals negative b plus or minus the square root of b squared. So 4 squared minus 4 times a, which is 1. Times c, which is negative x. All over 2 times a. And now that we have that, we get y equals negative 4 plus or minus the square root of, since we give us 16 minus negative 4 times negative x would be plus 4x all over 2. And then we can simplify this. So if I do some work over here, we have the square root of, I'm going to write this in order, so 4x plus 16. So that's the square root of 4 times x plus 4. And so this is really the square root of 4 times the square root of x plus 4, and the square root of 4 is 2. So 2 root x plus 4 is what the radical simplifies into. So over here we have y equals negative 4 plus or minus 2 times the square root of x plus 4 all over 2. And so that means we can divide each of these out. So that means that each term, which terms are separated by the addition and subtraction. So This would be divided by 2, and this would be divided by 2. So we get y equals -2 plus or minus the square root of x plus 4. And then for this one, we cannot use function notation because this is not a function. Every input has 2 outputs because of the plus or minus. So not a function. So don't use f inverse of x notation. And we could see that from the beginning because this is a quadratic function which doesn't pass the horizontal line test, which means your inverse is not a function. Looking at the next equation, this is a rational function, which this does pass the horizontal line test, so the inverse is going to be a function. So switch our x and our y's. So we get x equals 2y over y plus 2. Multiply both sides by y plus 2. So we get xy plus 2x equals 2y. And then we have to get the y terms together. I'm going to subtract that to the other side. So we have 2x equals 2y minus xy. Now the question is we need to get y by itself. So these are not like terms. When we're like terms, you have to have the same variables to the same powers to add the coefficients. So we have y in both these terms, which in order to get that by itself, we can factor it out. Remember, when you're factoring something out, you're just dividing it out, so it goes in front. So this would just be 2 minus x. And you can check your work. If you were to distribute the y back in, you would get 2y minus xy. And so then the next step is to divide by 2 minus x on both sides. And we can then rewrite this using our inverse notation. So f inverse of x equals 2x over, and you can write this in order, so negative x plus 2, or you can leave it as 2 minus x, but normally rewrite the x's first. So that would be my inverse. All right. It says two functions, f and g, are inverse functions if and only if both of their compositions are the identity function x. In other words, if you were to do the compositions and they both equal x, then they are functions. So when you get into upper level math, in order to prove or verify something, you want to use the definition. And the definition of an inverse function is using compositions of functions to get x out. And why are we getting x out? Because remember that the line of reflection is y equals x. Which is that identity function. So if you do something to your x values and then you do the inverse, which undoes it, you're getting just x out, which is again your line of reflection. So it says show that each function is the inverse of the other using compositions. So in order to do that, you have to do both compositions in order to prove or verify that these are functions. So we're going to have to do f of g of x. So we'll do that one first. So we're plugging g of x in for f. So when I plug that in and then simplify, this is really over 1. So you really have 4 times x minus 3 in the numerator over 4 plus 3. And notice that the 4's are going to cancel out because 4 over 4 is just 1. So you have x minus 3 plus 3, which is just equal to x. So this one checked out, but we're not done. Now we have to do also show g of f of x equals x. You always have to do both. So we have g of, and f of x is 4x plus 3. So here for this one, in the numerator, you can drop the parentheses and the 3's cancel out. So you get 4x over x, which that of course just equals x. So notice that both compositions are equal to x, the identity function. So the third statement would be, since f of g of x equals g of f of x, and they both equal x, and we have these three dots, which stands for therefore, or in conclusion, they are inverses. So you can pause the video and be on your own when you're done on pause to check your work. So again, we have to show both compositions. So for the first one, if I do f of g of x, we get f of g of x is 12 minus 9, or 12x minus 9. So we have 2 times 12x minus 9 over 5 in the numerator. And then we distribute and I just realized I changed this on your paper, so I made this 5 halves x minus 5. So let's go ahead and change that. To 5 halves x minus 5. All right, so when we simplify, 2/5 times 5 halves, that's just 1, because you get 10 over 10 x. So that's just 1x. And then minus, if you could distribute, this would be minus 10 fifths plus 5, which then gives us x minus 2 plus 5, which is x plus 3. Notice that that is not equal to x. So f of g of x does not equal x. Thus, f of x and g of x are not inverses. So you can stop after one doesn't work, because if it doesn't work for one, then you can't have inverses. It has to be able to work for both compositions, f of g of x and g of f of x. So then, like I said, you can just stop there and say that they're not inverses. So the last part of what we're going to look today is called restricting the domain. For a function that is not one-to-one, it is possible to produce an inverse function. So we're purposely making these inverses function by considering only a part of the function that is one-to-one by restricting the domain of the original function. So this is called restricting the domain. So these questions say, find an interval in which the function f of x below is one-to-one and find the inverse on that interval. So looking at the first one, we just have our parent graph for our quadratic functions, y equals x squared. So we know this is not one-to-one because it doesn't pass the horizontal line test. But where could we cut this off so that it would be one-to-one? The easiest place to cut this off would be at the vertex here. And if we cut off our graph there, we could either use the left side or the right side of the graph. So we could use this side. If we just use that side, it passes then the horizontal line test if the right side wasn't there, or vice versa. So that means this domain would be restricted to either negative infinity to 0 bracket, or if you were doing the right side, bracket 0 to infinity. So we could restrict the domain from negative infinity to 0, or 0 to infinity. And then you would have to find the inverse on that restriction. So how do you find the inverse? Switch your x and y's and solve. So we have x equals y squared. We're solving for y. So plus or minus the square root of x equals y, which is not a function. So if you were to graph the inverse, your inverse graph would look like this. Which you can see doesn't pass the vertical line test. So if we are restricting the graph to the left side or the negative values, then since those are negative, that would actually be this graph down here. So that would be the negative square root answer. So then f inverse of x would be equal to the negative square root of x. And if we're using the positive side, then we would get the positive radical answer on the top, which would be just the square root of x. And you can, again, think about that. Remember, these graphs are reflections across the line y equals x. So if I graph my y equals x line here, that's my line of reflection. So you can see how the graphs would reflect over then. So the next question is the same thing, except for we have x minus 3 quantities squared. Remember, that's a transformation moving your quadratic graph to the right. So now that means then if we were to cut the graph in half here at the vertex, we would be using our domain restrictions of negative infinity to 3 bracket or 3 to infinity. And then to think about the inverse, same thing. We have to first solve for the inverse equation. So x equals y minus 3 quantity squared. So we do PEMDAS backwards. We don't have anything add or subtract or multiplied or divided on the outside of what's being squared. So then you do the exponent and then what's inside parentheses. So to get rid of the square, plus or minus the square root of x equals y minus 3, and then add the 3. So 3 plus or minus the square root of x equals y. Now, a lot of the times you'll see me write the number in front of the plus or minus. You can write the plus or minus the square root of x and then plus 3. You just have to be careful because sometimes students then do this where they extend their square root over that value, which would be incorrect. But that's why I normally write it with the value in front. So if we are doing the negative side of the domain, you would use the negative square root. So 3 minus the square root of x. If we're doing the positive side, then you would use the positive square root, so 3 plus the square root of x. So those would be restricting the domain. And if it helps you to actually then graph the inverse, you could to see that that is reflected across the line y equals x. So I graph the inverse real quick just to see. So again, if we're using the negative side, so this here gives us this graph, the negative reflection, and then this side of our parabola would be this one up here, because again, remember, it's reflected across the line y equals x. And that is it for our inverses and functions.